Hey folks, Ms. Gosling here. In this video, you're going to learn about wind power. By the end of the video, you'll be able to quantitatively analyze the energy provided by wind turbines. So let's go ahead and get started, shall we? So what is wind power? Wind power uses the kinetic energy of the wind to generate electricity. So essentially, that's the spinning of the rotor, so of the blades of my wind turbine is also spinning an electromagnet in a generator, generating electricity. So some pros. Wind energy does not exacerbate climate change. It's renewable and it's easy to maintain when on land. Um, Unfortunately, offshore wind, which is generally more reliable and more efficient, is less easy to maintain. Some cons though, the output is variable. So on a windy day, you'll get a lot more energy than on a not windy day. There's also limited site availability. So for example, wind turbines do much better on the tops of hills than they do in the depths of valleys. And so if you don't have enough hills or if you're in an area with not a lot of wind, it may not be worth it to put in a wind generator. Some folks also complain of noise pollution or think that wind turbines are ugly, and there are potential ecological impacts. So we don't know a ton about the potential ecological impacts of wind turbines, but it's something we always want to take into consideration when we're thinking about what energy sources are most efficient. So to figure out the power generated by a wind turbine, what we need to know is what is the um, mass of air moving through the turbine every second, because our power is actually going to be directly related to the kinetic energy of our wind. So what we want to know is the mass per second passing through our turbine, and that is going to be equal to the density of our air times the speed of the air times the area that our wind turbine is sweeping out. And you'll notice here, guys, our density is given in kilograms per meter cubed. The wind speed is in meters per second, and our area is in meters squared. So that gives us our units become our meters cubed will all cancel. Our meters will cancel, and that's going to give us kilograms over seconds, which is, of course, mass per unit time. So the power of my wind turbine is given by 1/2 times rho times V times A times my speed squared. So my power is then 1/2 times the air density times the area swept out by my wind turbine. So here, let me pick a slightly nicer color here. So the area kind of here, this is not a great angle for it, times V cubed, the wind speed cubed. Or if I know instead the radius of my wind turbine, so the length of one of the blades, I can rewrite my power equation as P is equal to 1/2 times the density of air times pi times my radius squared instead of area times my wind speed cubed. And let me go ahead and take a moment to just label everything in my equation. So again, rho is my air density, R is going to be the blade length, and V is my wind speed. Thus giving me the power generated by my wind turbine. So moving forward, let's go ahead and look at a theoretical question. So we know that power is equal to 1/2 times pi r squared times the density of air times the speed of the air, the wind speed cubed, divided by our time. So our question is, what happens if the wind speed doubles? So if v goes to 2v. Well, let's take a look. So we'll say power is equal to a constant times v cubed, where our constant is this whole thing here. So if V is doubled, then we'll say something times our power is equal to, or so if our is equal to our constant times 2V, that whole quantity is cubed. So we know that 2 cubed is 8, so our power is going to get multiplied by 8. We're going to have 8 times the power if the wind speed doubles. So we can see here how dependent the power generated by a wind turbine is on the speed of the wind. So let's look at a slightly more quantitative problem. A wind turbine with 25-meter blades is in a location where the average wind speed is 11 meters per second. What is the maximum energy output of the wind turbine? The air density is 1.3 kilograms meters cubed. So here, our givens are the radius of the wind turbine, which is 25 meters, the wind speed V, which is 11 meters per second, and the density rho, which is 1.3 kilograms per meter cubed. We also know that our unknown is the theoretical maximum output energy. So our output energy if there is no concern, if there are no concerns about efficiency. So E out. So our equation here is going to be given as E is equal to 1/2 rho pi r squared v cubed. Thus, when I sub and solve, what I will write is that my energy is equal to 1/2 times 1.3 times pi times 25 squared times 11 cubed. Thus, my maximum energy output is approximately 1.7 megajoules, or my potential energy output is 1.7 megawatts. And there we go. That is how we can solve our wind turbine problems. So moving forward, wind turbines are a renewable source of energy. The power produced by a wind turbine depends on its blade length, as well as on wind speed and air density. And there you have it, guys. You now know how to solve wind energy problems. It's your turn to try some on your own. Best of luck and happy solving.